Good afternoon, dear students. We completed till compressibility factor yesterday, and today we are going to move to the next topic, which is liquefaction of gases. So in this portion, we are going to discuss about conversion of gases to liquid, or how we can convert a gaseous form to liquid form. We are very familiar with these states, gas and liquid. In gaseous state, the molecules are very free to move, they don't have much interaction between each other, and they occupy the space of the whole container. In case of liquid, they have much more interaction between molecules than that of gases. So we are going to convert this form to this form. That is what is known as liquefaction of gases. And for that, what we can do? So to bring them closer, we have seen some methods in the previous classes. So what were they? Either we need to decrease the temperature or increase pressure. So if we want to convert a gas to a liquid, either we need to decrease its temperature or increase pressure. But there is a problem with increasing pressure. When we usually increase the pressure and the molecule come closer, there is repulsion between the particles. And to cover up that, we need to decrease the temperature so that the energy of these decreases, hence interaction becomes possible. So out of this, main point is decreasing temperature. If temperature is not done properly, increasing pressure will not help. And now we are going to discuss about an experiment or a famous experiment which did the liquefaction of gases. So we will discuss that now. A complete data on pressure, volume, temperature relations of a substance in both gaseous and liquid state was obtained by Thomas Andrews on carbon dioxide. So a scientist named Thomas Andrews worked his experiments on carbon dioxide. And what he was trying was, he was trying to convert carbon dioxide gas to liquid form. And during his experiment, he changed the pressure, volume and temperature, or he was altering the pressure, volume and temperature accordingly so that he will get the carbon dioxide liquid. So he did an experiment on carbon dioxide to convert carbon dioxide gas to liquid with varying pressure, volume and temperature conditions. And as a result of his experiment, he got this graph as his product. So this graph tells us about the liquefaction of carbon dioxide and the experiments which he did. So we will see what are the experiments he did. So we will start from here. So first what he did was, he took carbon dioxide at 50 degrees Celsius and started increasing its pressure. So initially the volume was this much, and as he started increasing the pressure, it increased till this point, and it does not change to liquid at all. And as he increased the pressure, volume started decreasing and pressure kept on increasing. So pressure increased but volume decreased. That is a known fact which we know. When pressure increases, volume decreases. But initially he started with a gaseous state and finally ended up again with gaseous state only. So at 50 degrees Celsius he didn't see any change at all. And then he reduced the temperature to 31.1 degrees Celsius and again started the experiment. So this time again he started at this point of volume and started to increase the pressure. So when pressure increased, the volume decreased from this point to this point. So volume is decreasing, pressure is increasing, but there is no change in the state. He started with the gaseous state and again ended up with gaseous state only. So this experiment initially tells us that if the temperature is not apt for the experiment, then how much ever we decrease or increase the pressure, they will not change its state. Volume might change, but the state or the liquid state is not getting formed from the gaseous one. So temperature is very important there. So what he have done? Initially he took the carbon dioxide at 50 degrees Celsius and started to increase the pressure of it. So as the pressure was increasing, molecules or particles were coming close but it was not converted to liquid form. The volume was decreasing. When pressure is applied, volume is decreasing, but there is no change in the state. Second thing also, the same thing he did, but the volume changed from this point to this point. So this much volume was decreased according to increase in pressure. But there also you can see there is no change of state. So volume is decreasing according to the pressure, but again there is no change from the gaseous state to liquid state. Initially it was gaseous, finally it was gaseous only. And again in the third experiment, so he is decreasing the temperature again. Initially it was 50 degree, then he decreased to 31.1. Now a slight decrease he is giving, 31.1 degrees Celsius to 30.98 degrees Celsius. So at this temperature, it is just a slight difference, right, from 31.1 degree to 30.98 degree. So in this temperature, when he compressed the gas from this point to this point, suddenly when it reached this point, it changed to liquid state. So it was a sudden change. So at 30.98 degrees Celsius, when he took carbon dioxide and started applying pressure, so what happened? It decreased the volume from this point to this point, and particularly at this point, it suddenly converted to liquid form. So the gaseous carbon dioxide converted to liquid form in this state. He still increased the pressure and it undergone a little bit of compression also. But initially when he increased the pressure, volume was converted from this much to this much. But after this point, if you see, it is just a slight decrease from Vc to V3 here. So this amount of decrease is more than that of this decrease. Why is that so? Because after in this point the carbon dioxide was in gaseous state. So compression is easy. So as he applied pressure, the volume was decreasing suddenly or in a more quantity. So from here it is decreasing, the volume is decreasing as it is applying pressure, reaches an extent and again converted to liquid at this point. So once it is converted to liquid, further compression is not possible or it is very difficult to compress liquids that we have seen. Already they are liquefied or converted to liquid form. So still compression is very difficult. So that's why after this point, increase in pressure will not cause much decrease in volume. So that is why from this point to this point we can see a bigger decrease in volume, but from this point to this point we can see lesser amount of volume decrease. So coming back to the liquefaction, at particularly 30.98 degrees Celsius, particularly at 73 pressure, the gas was converted to liquid. So isn't this points important? Yes, it is very important. So these points are noted as this temperature is noted as critical temperature. So this is the temperature at which the gas or the gaseous carbon dioxide was converted to liquid form. And this is the pressure where the the gaseous carbon dioxide was converted to liquid form, and that pressure is known as critical pressure. And at that time of critical temperature and critical pressure, if we have taken 1 mole of gas, how much is the volume remains at the critical temperature and pressure? That is known as the critical volume. So again if I tell, so what is the temperature where the carbon dioxide is converted to liquid form? That temperature is known as critical temperature here. And this is the temperature or this is the maximum temperature at which a gaseous carbon dioxide can be converted to liquids. So above this temperature, just above this temperature, if it was 30.98, and when we converted to 31.1 also, the conversion of from gaseous state to liquid state was not possible, right? So we took it from 50 degrees Celsius, we decreased it up to 31.1 also, but still it was not getting converted. But as it reached 30.98, this particular temperature, the gaseous carbon dioxide was converted to liquid carbon dioxide. So we can tell this is the temperature at which, or this is the maximum temperature at which the gaseous carbon dioxide can be converted to liquid form, and that temperature is known as critical temperature, and the pressure at critical temperature is known as critical pressure. And at critical pressure and critical temperature, if we have taken just 1 mole of gas for this experiment, and how much ever is the volume at critical temperature and critical pressure, that volume is denoted as critical volume. So again, at critical temperature and critical pressure, if we would have taken 1 mole exactly, and what is the volume remains at critical temperature, that volume is known as critical volume. So we can take how much ever volume we want, right? If we take 100 liters of gas and finally after conversion it can be 10 liters. So if we take 500 liters of gas, it can be 50 liters. So we can take how much ever liters or how much ever volume we want in the initial stage. So that's why we are telling 1 mole. 1 mole if we take, and how much is in the final stage of conversion, that much is known as the critical volume. So we will see the definitions there. Critical temperature of a gas is the highest temperature at which the liquefaction of gases occur. So at more than this temperature, liquefaction is not possible. Volume of 1 mole of gas at critical temperature is called critical volume, and pressure at critical temperature is called critical pressure. So now we have told that this is the maximum temperature at which the carbon dioxide can be converted to liquid form. So this is just for carbon dioxide. Every gas has its own critical temperature. Like the boiling point and melting point, the critical temperature is also particular for particular gases. With this, Thomas Andrews didn't complete his experiment. He further decreased the temperature below the critical temperature. So critical temperature is the maximum temperature at which the compression or the conversion of liquid or conversion of gas to liquid is possible. But below that also we can convert gas to liquid form. So he carried out an experiment again. There what happened was, this point he took the CO2 molecules under 21.5 degrees Celsius and started to increase the pressure. So pressure was increasing and slowly the volume was decreasing. But particularly at this point of B, the gaseous molecules of CO2 started to convert to liquid, but it was not like a sudden conversion from gas to liquid like in the case of the critical temperature, but slightly it was started to convert. You can see a dome here, right? So this is the dome here, which indicates the gaseous and liquid form together exist there. So at the point of B, the gaseous molecules of CO2 was converted or started to convert to liquid form, but not fully converted to liquid form. And there you can see the pressure is remaining constant. So what we can observe here is, at point B, if we have taken 100 molecules of CO2, gaseous molecules, 50 of them, not 50, but 10 of them was converted to liquid form, but 90 of them remained as gaseous only. And further when we convert, or further when we increase the pressure slowly and slowly until it reaches this point, this gaseous form is converted fully to liquid form. So in the critical temperature, at this point, all of a sudden all the molecules converted to liquid form. But in this case, at point B, it started conversion, and until the point C, it converted to liquid form. So initially it was 10 molecules, then it was 20, 30, 40, and particularly at this point, all the CO2 molecules which we have taken here is converted to liquid. Initially, it was not fully converted, and throughout this process, it was converted to liquid, and at C, it was fully converted to liquid form. And here you can see a plateau. And through this conversion, pressure is not changing at all. Here, volume is decreasing but pressure remains the constant. But after point C, again pressure starts increasing to an extent. But volume, if you consider here also, from this point to this point you can see a huge decrease. But after this point of C, after complete liquefaction, the volume which is reducing is much lesser than this quantity. Because here all the gases are converted to liquid form and further compression of liquid is not easy. So that is why after this point, as the pressure increase, volume is not decreasing much. So again here you can see one more experiment at 13.1 degrees Celsius. Again he is decreasing the temperature and doing the same experiment. There also you can see at this point the conversion of gaseous form to liquid form starts, and throughout this the gaseous and liquid form coexist. Or inside this dome you can see both liquid form and gaseous form together. Here the percentage of gaseous form will be higher, and when you reach this stage you can see more of liquid than that of gas. So in this case also the same thing happens. After this point it is starting to convert to liquid form. So in this portion you can see more of gas, and further when we reach this portion the gaseous form is almost completely converted to liquid, and here the liquid form will be more. At this point all the gas is converted to liquid and again increases pressure. So if you see inside the dome, as we decrease the temperature from the critical point, the area of the dome or area of the conversion is increasing, right? So initially it was just this much, but then it increased to this much area. And at this stage the pressure remains the constant. After conversion of fully the gaseous state to liquid state, then only pressure increases. So that's all about his experiments. So at this point of time, we do have a question in our mind. So is it possible to change a gas into liquid by a process in which without entering the intermediate state? So the question is, if we can convert a gas at temperature at this stage at 21.5 we can take. So at stage A, can we convert this gas to a stage where it is completely converted to liquid, or the state D, without entering this stage? So without entering the intermediate stage, can we convert this gas to complete liquid? And that is a question, and the answer for that is a big yes. And how is that be done? This is actually similar to that of taking a long route in a journey. So from this, actually going like this is the shortcut, but we are going to take a long route. So what we are going to do, at point A the temperature is 21.5 we can assume. So at this temperature we can't go to point D without touching B and C. So we are increasing the temperature to 31.1 degree. So we are reaching this point and again started increasing the pressure. So from this point of F, it is converted to G, right? So A to F we are increasing the pressure, at F we are increasing the pressure, hence it will go to G, and after G we compress the gas and decrease the pressure, and hence we will reach the point D, and D is the point where we get complete liquid. So first we increase the temperature, then reach a point with increasing pressure, then compress the gas to a liquid form. So with this we can avoid this route or the intermediate stage. And in this figure you can see different critical temperature, pressure and volumes of different gases. So as we told, different gases will have different critical conditions, and you can note it down in the notes. So with this what we have learned is, gases need to be compressed below their critical temperature. Above the critical temperature, even if we increase the pressure to the maximum, we will not get liquid stage. So below the critical temperature only, we can compress a gas or liquefy a gas. So with that, we conclude the session, and you have to make sure that you include points from textbook also while writing the notes. Thank you.